is the one more example for Hohmann transfer, and this is my notes. This example is from another book, and I just make a copy and for everyone. And this is a very practical exercise, and the purpose is just want to show right now you should have the very good capability of doing something. Okay, and of course the fine-tuning will be necessary, but I think everyone should have that this kind of knowledge can really do something. Okay, so for this one, basically the idea is this is the mission to the moon, and I always be confused with the terminologies, but anyhow, there is a mother craft, and they're circulating around the surface of the moon, and this is the module that went onto the surface. So basically, 3 astronauts, and one is operating the mother space, the craft and surrounding, and 2 astronauts on the launching module and onto the surface, and then they met aliens and then escape away. They actually NASA stopped the moon's missions. Okay, so basically I believe that this is something there. So they stop. Okay, but anyhow. So once they finish their missions, then basically the launch modules they went to burn off and to come back to the surface and then to meet the mother spacecraft and then going back, then going home. So basically here is the process and how they maneuvers and to meet together. So here is for the whole missions in brief is this, and this is the module from here they launch and then go to the certain elevate and into a transfer orbit, and hopefully at a certain period of time they will meet the mother spacecraft at this point. Okay, so that is the mission. And you don't have to do this one. Maybe you can design your the rendezvous point here. Okay, but here we simply take for example, if we launch to here, if we take this is the say perigee distance, then if we take only half cycle, okay, so that is our options. And so for this case, we do want to for this problem we want to have these questions. So the first one, what is the burnout speed of the LM? LM is the lunar module here. Okay, so the burnout speed is here, and so that one we can calculate based upon the information. And so, for example, here I simplify the problem statements into these figures, and that I believe that is a copy on the handouts here. So here, for example, the R1 is to measure from the focus to the point where the burnout, and that is given by this value. And R2 is the distance at there they're going to meet with the spacecraft. So that is the information. So with the 2 informations we can quickly calculate is this, and that is 8. I will try to match the terminologies to the calculations, and so let me do this one. How about let me draw this one here one more time. Okay, so this is the focus here. So this is R1, and this is R2, and that is the transfer orbit. Okay, so let me call this is orbit 1, and this is orbit 2, and this is the transfer orbit T. And there's a handout on the table at the front. So here at this point here, we can calculate velocity, and velocity at orbit 1 and at r equal to r1, so which means right now I focus on this point here. So that one, we're assuming that is the circular orbit. So the velocity equal to u divided by r. Okay, and here we plug in all the information. So basically r equal to r1 here. Let me do this one. So r equal to r1. Okay. And because here our the main is not Earth, rather than that is the moon. So here we have to take the moon for this constant. Here we can check out from the table. That is 4.83503. Okay, we take out these numbers, then we can calculate. I don't have that one, so can I just read it for you? Okay. The second one we can calculate is the on the transfer orbit. Okay, T means the transfer orbit at r equal to r1. And that one, because the transfer orbit is elliptic orbit, so we have the equations is 2 mu r minus mu over a. So for this case, the r equal to r1, and a basically is the average is the semi-majors. So basically a equal to r1 plus r2 divided by 2. Okay. So this one is what we can calculate. This is we call the burnout speed. I try to match the information here. Okay. So this one we can determine is 1.7004 kilometer per second. And the second one, what is the magnitude of the lunar required to rendezvous? Okay, so that one we can continue at this point here. So right now at this rendezvous point, so v velocity on the orbit 2 and at r2, and also we need to calculate the velocity at on the transfer orbit at r equal to r2. Basically here we want to calculate what is the difference of the speed at this point, then we can determine the delta v. Okay, so that is idea. So on the second orbit, and that is a circular orbit, so again we plug in these equations here. Okay, so that is 1.5587. And for this one, that is the elliptic orbit, so we plug in this equation r minus mu over a. So here the r equal to r2 and a equal to the average of that one and say r1 plus r2 divided by 2. So this number is 1.5124. So therefore, for this case, what is the magnitude of the maneuver required? So I think this one is just asking, we're going to calculate delta v there. So delta v equal to 1.5587 minus 1.5124. So this one is 0.0462. Okay, so from here that can help us estimate how much fuel we need to bring for the lunar module there. Okay, and part C, what is the checking the coast time? So that means the time spent from here to here. Basically, that is a half cycle, the half period of the elliptic orbit. So for this case, the C that basically is the phasing time. Equal to the half of the cycle. So basically that is 1/2 times 2 pi times A3 divided by mu. Okay, so here the A is the R1 plus R2. That is for the transfer orbit. Okay. So that is for the transfer orbit. So here we can do the calculation. So that is 3682.8 seconds. Okay. Okay. Then I can wait for a few seconds and then let you to finish the writing there. And the last one, if you have time, you can begin to read the last problem. The last problem is to ask when is the time we need to launch in the way we will guarantee the two craft will meet here. So the last question basically asking is this: the time spent from here for this craft on the orbit from there to here must be the same time, the same amount of time for this one to spend on this orbit from there to here. Okay, so right now in the part C, we already determined the time spent from here to here, which is the calculated there. So now we simply using that information to see how much we can back on to see, we can determine what is the relative positions for this spacecraft and on this position there. So that means that can help us. So right now here we want to determine is if this is a spacecraft here and is moving from here to here must be equal to the same amount from here to here. For this one from here to here. So that is determining is the time equal to 3682.8 seconds. So that means we have to kind of timing the launching time, otherwise they won't meet together. So from here we can determine. So for this one, this is the circular orbit. So the circular orbit period for the period 2, we can determine is 2 pi divided by the radius. We plug in that formula. Okay. So for the second period, the A simply equal to R2. Okay, and mu equal to the same number. So from here we determine the period equal to A021.5 seconds. So making the whole loop need that much time, and if we only need that much, so from here we can determine this angle. So that means this angle we can determine is simply say 3682.8 seconds divided by A021.5 seconds multiplied 360 degrees. And in this way we can determine this angle. So that angle is 165.28 degrees. So that will help us to determine when we need to launch this module. Okay. So this information will help us to determine, and that is the same example like we did last time for mission to the Mars, and when will be the good time to launch from the surface of the Earth. Okay. So this is a very quick example for showing this.